Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Get that started. It is my pleasure today to introduce Ravi Sundram, who will be telling us about stealing cycles in the cloud. Ravi is a professor at Northeastern University, where he's focused on an incredible wide range of security and systems topics. I don't even think I can think of them off the top of my head. And he'll be talking today about some joint work it's of great interest to all of us. Thank you.
Okay, thanks, Dave. So thank you, everybody, for coming for this talk. It's a great honor and a great opportunity. So thank you very much. So this is I'll be talking about this essentially a bug that we found in the Zen hypervisor, and it's also existent in Amazon's EC2, so that you can steal cycles. And that's what I'll be talking about. This is joint work with Peter Desnoyers, who's sitting in the back. Peter is a systems guru, so if you guys have questions, you should definitely ask me, but Peter may end up answering the questions. And then to grad students, Manish and Fongfei. Okay, so this is the outline of the talk. I'll go quickly over virtualization and cloud computing. Most everybody knows that. Then I'll talk specifically about our bug, the attack, and how we can steal cycles. Then I'll talk about the Zen scheduler, which is where this bug exists, and then how you can fix it, some of our solutions. And then I'll present a nice combinatorial problem. There's at least one theorist, David, in the room, so you may get a kick out of that, the theory stuff. Okay, so let's start. So virtualization. Virtualization, it's an old idea. It's if you look on Wikipedia, virtualization has been around from the 1960s. It's basically you simulate on software the hardware resource, and that's what virtualization is. But then it got a real lease of life, a new resurgence in 2000 with VMware, and that's when sort of virtualization came back into its own. It became very popular because people had multiple systems, a sprawl of systems, and virtualization gave lots of benefits. I'll talk about that briefly. So today, virtualization, there's an explosion. Everything you can think of, people talk about virtualizing it. There's virtualized storage, virtualized network, virtualized database, virtualized desktop. We'll be focusing on virtualized servers. Okay. So the benefits of virtualization, you get better utilization. So you can pack more virtual machines onto one physical machine. You can migrate things from one place to another. These were harder to do earlier when you had an OS stuck to the hardware. And management has supposedly become easier with virtualization. At the same time, it has costs. Things get slower. You can't, because the hypervisor takes up some space, you can't scale as many things. With the same amount of hardware, you're doing less computation. And in some sense, management becomes more complicated because now there are more things that fail, managing virtual machines, managing the sprawl of virtual machines. You have to take that into account in your design. People move things around. So on the one hand, it eases things. At the same time, it also complicates things. Okay, so basic of virtualization. So normally you have the operating system that mediates access to resources. Now you have something called the hypervisor or virtual machine monitor that sits over the hardware, and it mediates access to the resources. And there are different types of virtualization. People roughly break it into these four types. They have three types. Emulation. So there you just simulate the virtual machine's instructions step by step. So people have just-in-time emulation and so on. So it's gotten faster, but it's somewhat slow. You're not actually giving control to the instruction pointer to the VM. You're sort of managing the VM's execution. The hypervisor is managing the VM's execution. So it's a step-by-step emulation. But on the other hand, you can emulate anything you want. You can emulate any hardware you want. Para-virtualization, here the virtual machine is actually modified a little bit. So you can't run a native operating system, the virtual machine. You have to modify it. Some of the calls you have to change. and the guest OS is modified to use hypercalls. There's an API called the Para API, and so you have to change things to fit that API. And the hypercalls are trapped by the hypervisor, so that's how the hypervisor knows when to. That's how the hypervisor gets control and then manages resources and then gives back control to a different virtual machine potentially. And then in about 2005, 2006, Intel came out with the VT, Intel Virtualization Technology, so normally before there was in the CPUs, there was user and supervisor mode. Now they put in another mode called hypervisor mode. And so you could give in the CPU, in the hardware, control to the hypervisor. And so this made it easier. You could have an unmodified guest OS. And so that is a hardware virtual assist. Okay. What is cloud computing? So cloud computing is this new metaphor or buzz phrase that's there's mainframe, then there's client server, and today everything is cloud. It's basically it's a still evolving definition. It's cloud computing, dynamically scalable resources provided as a service over the internet. That's the Wikipedia definition. And some characteristics: on-demand self-service. You should be able to set up service for yourself. It's got good network access. There's resource pooling and rapid elasticity. That means that all the physical hardware is pooled together as a resource, and there's rapid elasticity, meaning you can scale it dynamically. And then there's measured service. So they meter how much you use, and then they charge you for it. So that's cloud computing. And this resource pooling and rapid elasticity, that enabling that, the underlying technology is virtualization. So virtualization is a big part of clouds because it enables you to seamlessly move things across different physical hosts and make the entire collection of physical hosts, abstracts it away as one common layer. So virtualization is useful. Okay. Here are some cloud computing service providers: Amazon, Windows, Azure. If people count Zoho, Salesforce, all of these companies.
Do they have a service, or do they just have software? Can you buy cycles from them?
So they claim that. The last I saw was a press release in mid of last year, where they said that they're actually going to be selling a service. Do you know? Have they since? Right.
I don't know if it's not.
I haven't seen. You can't go by.
Because the main part of their business actual plan is actually not to run the services themselves. But
I see. But they put out a press release saying they are. They've even got a name.
They put out lots of press releases.
They at least had a group of people developing it, getting it ready to whether they were going to spin it off to someone.
Okay. Okay. So now basically, let me tell you about this bug we found. And to tell you about that, I'll tell you a little bit about Amazon's EC2. So Amazon's EC2, they use a customized version of Zen. So they say that in their web page. They say it's a proprietary version of Zen that they use. And it's in para-virtualization mode. You can sign up for an account. You sign up for an account, and then they have pre-built instances of Linux, Sun Solaris, Windows Server. And you can fire up those instances. You can see there's a menu. You can say I want a particular so many instances, and you fire them up. Now, some of the information I'm providing is a little dated. This was as of the research when we did last year, middle to late last year, middle to summer to fall. Things have changed slightly since then. At that time, there were two regions. There was US and Europe, and there were 3 availability zones. Availability zones seems like maybe different data centers in the same region. So they recommend that you fire up your machines, and if you really want your system to be fault tolerant and up and running, then you use multiple availability zones so that if one availability zone goes down, you still have it running up elsewhere. So that's EC2. And as of last year, this is how they were selling it. So you could go to your to the menu, and you could say, I want a small instance. And if you ask for a small instance, you'd get a 32-bit architecture. You'd get 1.7 gigabytes of memory. You'd get 1 core. And the speed, they have something called EC2 compute units. And that's some EC2 term. Roughly, if you want to think of it, you should multiply the number of cores by the speed, and that's the amount of computation you have. in that instance. So here you can think of it as 2 times 2.5 or 5 amounts of computation. Okay, and this is how much they charge you for that. So you fire up your instance, they look at wall clock time. If you run for 1 hour, you pay 10 cents for the small instance, you pay 20 cents for the medium instance, and so on.
And the memory is the actual physical memory that backs the VM.
That backs the VM, correct. That's the physical memory that backs the VM. Exactly, correct. Yeah. Again, as David was pointing out, when you run on the cloud, there's no attestation, or we really don't know if you're getting what you're supposed to be getting, and that's sort of at the heart of the bug that we'll be talking about, but this is what they promise you. Yeah?
When you say the measurement, I mean, I'm not familiar with the charging model, but is the measurement based on wall clock time or essentially all the execution time? So for example, if your process is temporarily suspending, so for example, waiting for I/O or waiting for memory,
correct,
then are you still paying for that?
Right now, you're still paying.
But that's the interface you're giving to the user, right? Because internally they could have oversubscription. You could have actually have your application, my application running on the same
correct,
single instance.
Correct.
They'll still charge us.
They still charge you. Once you fire it up, until you shut it down, they charge you whether you're blocked or whether you're running. That's the current model. Correct. Okay, so here is the main result. So we can take a virtual machine and we can modify it slightly so that we can create an attacker out of it, which will consume more cycles than it should actually. So if you'll see here, the way it evolved was we found this attack on Zen. We were poking around in Zen, we were looking at the code, and then we found this bug. Then we said, we knew that Amazon was using Zen, so we said, okay, why don't we poke around and see if the bug exists in Amazon? And then we found the bug existed. And then we were a little afraid because we found we could eat up a lot more cycles than we were actually being provisioned for, and we didn't want to impact other customers. So then we actually got in touch with John, and John put us in touch with somebody at Amazon, who they then set up a separate physical machine for us. So that when we run there, we won't be impacting other customers of Amazon. So they provided us a single 4-core 2.6 gigahertz system. So we have a bunch of measurements that we did on the regular EC2, but we were in contact with Amazon. Then they gave us this separate machine. We also sort of agreed that we wouldn't those measurements in the regular EC2 we wouldn't publish it, and since then, they've also put out a patch. So these are on the hardware that Amazon provided us. So what you see is we can take a standard instance, a small instance. We took a small instance, and we can sort of jack it up so that it consumes north of 80% of cycles on that machine. And here we run more and more victims. So these are not regular VMs that are not jacked up in the same way. And what we found was, yes, we were stealing cycles, but we were stealing cycles from Amazon, not from other customers. So you see the victims are holding pretty steady. Okay, so they're supposed to get about 40%. So that when Amazon says they'll sell you 1 core, they are selling you like 40% of a core. That's what they're selling you. Okay, and so when we instrumented it and looked at, we used this thing called Drystone, which is a benchmark, standard benchmark, and we ran it and saw how many cycles we get. Then we can, if we jack it up, we can get close to 100% of the entire core, whereas if you run a regular small instance in the usual way, you are capped at about 40%. So they have somehow modified the Zen hypervisor so that they're capping you at that 40%. Okay. And so this is on the on EC2. Okay, let me show you what happens on Zen. Yeah, go ahead.
It seems like in the case where you have you and 1 victim, you're getting a total of like 120% of CPU.
Correct. So this was on you and 1 victim. So we have 4 cores. Okay, so each core is 100%.
Oh, okay.
So when I run out at 4 times 2.5, which is 10, when me plus 9 victims, then we'll all be hitting 40%. After that, we'll start sinking below 40%. Okay. So yeah, so that's a good point. So one core is 100%. Okay. With Zen, you can actually see that we are actually eating into the victims. So here, in regular plain vanilla Zen, not the Amazon hardened Zen, if we run our attacker, we are steadily.
Do you have access to the source code for Amazon Zen?
No. So Amazon, they were very cagey in all their the con calls and the emails back and forth. So the way the evolution went was, so John connected us to somebody in their group. We were told that the core group is out of South Africa. So then we were in some con call with them. They set up this machine. We gave them our attack code, which I'll show you. And then they verified that there was this issue. Then after that, they rolled out a patch, and then we tried attacking the patch, and we couldn't break it. So the patch seemed solid. And in all of this, we were trying to sort of talk and try to find out exactly what they were doing, how they were capping it at 40%, and so on. But they just sort of asked us for stuff, but they never disclosed any information to us at all. So that was the interaction. And in the case of just plain vanilla Zen, which you can run in the lab, what we see is that when we run in attack mode, we can consume all the cycles, and the victims steadily get less and less. If you look at this case here, the attacker is getting slightly less than the victim because we are running on a 2-core machine. That's 200%. So potentially, both of them can run 100%. But this guy, the attacker, is slightly less because there's a little bit of overhead associated with attacking. So you don't get the full amount. You get fewer dry stone cycles. Okay. So let me just show you I'll explain the attack to you. It's a very simple vulnerability.
This was not fixed in the main Zen.
No, it's still not fixed. So it's still.
But you notified the Zen boys.
So we haven't notified the Zen people. There's a Zen group, and there's Zen. There's some other lead people. We were thinking that we have a bunch of fixes in our paper. We were thinking that once our paper gets out, then automatically they'll fix it. At this point, no, we should notify them. Yeah, it's a good point. The people to whom it matters most is typically in the case of Zen, people are running in-house clouds. So then you're stealing from one hand is stealing from the other hand. Yeah.
Rackspace is not. They're using Zen for cloud services that they're selling to end user right now.
Okay.
So it would affect their business.
It would affect their business. Okay. 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 So it's a good point. We should tell the Zen people. Yeah.
On the previous slide,
Yeah.
Is there a cap on how much your attacker can? Because so if you go in the right figure, if you go from 0 instance to 1 instance, right?
Yeah.
So attacker is actually not gaining any more, because this is
Correct.
throughput measure, right? So
Correct.
is there any cap on how much any single instance? So even if nobody else is running, is there a cap on how much I can?
You can get one core. One instance can get at most 100%. It's the max you can run. And then the VMM chews up some cycles. The hypervisor chews up some cycles. So that's the only cap. There's no other cap. So here we are measuring the number of dry stone loops per second. Right? That's on the y-axis. You're saying, in general, if I have, say, like a 2-core machine, right? One virtual machine can just run permanently on one core without being taken off. And that's the most you can get. Sorry, maybe I didn't understand your question.
I guess I'm still trying to understand. So she's saying, okay, so the difference, if you look at the x-axis that one video here, if the attacker is running with a single victim, essentially you have this overhead because you're paying overheads for the attack. Right?
Correct.
But when there's no other instance running, you're essentially still saying that I can get maximum a single core.
This attack.
For one attack thing, but you get co-located with 4 of those things, and you end up paying half of what you should pay. And it does scale.
So essentially, if you get 4 cores, essentially you're bound to multiply that. So it's a normalized curve rather than an absolute, right? So essentially, it's normalized per core curve.
Normalized per core curve. Correct. Exactly. So you're going to say something?
Yeah, so was this running a single processor version of the kernel, or was this running a multi-processor version of the kernel in the guest?
Single processor.
Okay. Does
Oh, which kernel? You're talking the guest?
Well, yeah, I'm talking about the guest kernel.
Yeah.
Does it scale to multiple CPUs or not?
So we haven't. It should.
On the other hand, just keep in mind for the pure scalability argument, if you had 4 applications for the cores, you still get the 2-to-1 improvement. Just
Yeah, but you might have to have 4 instances running as
That's right.
opposed to 1 instance
That's
running
right.
the whole machine.
that's right.
Right, then you just do the thing where,
So if you have multiprocessor instance,
Yeah.
you have to time your sleeps. I'll have to think about that. Okay, so what is this bug and how are we exploiting it? So the basic bug is the way Zen works. It gives these virtual machines some credits, and then it runs each virtual machine on a particular core, and periodically comes back, looks at that virtual machine, and debits a certain number of credits from its account. When a machine runs out of credits, then it gets taken off, and other virtual machines keep running. Periodically on some schedule, it fills money credits back into everybody's account. Okay, so what we are doing essentially is we are taking this virtual machine and we are making it go to sleep at certain points. Whenever the scheduler is coming back, the hypervisor scheduler comes back to check, to take credits away, at that point this virtual machine goes to sleep. So its credits don't get drained. The virtual machine, when it gets taken off, somebody else gets put on, that person's account gets hit. And then this thing comes back from sleep, it wakes up, and unlike with operating systems and processes where an operating system can know whether a process is being woken up because of an I/O event or because of a self-timed sleep wake-up, with a virtual machine, an hypervisor can't tell. It's completely bundled inside this operating system. So it can't tell whether it's waking itself up or somebody else is waking it up from an I/O event. It doesn't have visibility inside it. So what happens is that in the case of the hypervisor, this effect is amplified where as soon as you wake up, you're put back again in the run queue and you immediately start to run. And then, again, you figure out when the guy is going to come check on you. You go to sleep at that time and you avoid getting charged. So that's the basic hide. I sort of put it to this train ticket scam. You're on I use this analogy. You're going on a train, you don't want to buy a ticket. You get on the train. When the ticket conductor comes, you go hide in the restroom. When the ticket conductor goes away, you come back and sit on your seat. There's a Bollywood movie in which there's one sequence in which what happens is there's like these 3 very smart guys who get on a train, then they buy just 1 ticket, and when the ticket conductor comes, they go into the restroom, all 3 of them. The ticket conductor knocks, they give that 1 ticket, and then the ticket conductor leaves, they come and sit down. And then there's this other guy who's not so book smart, and and these other 3 guys who are not so book smart. And what they do is they wait for these 3 guys to go into the restroom, then they go knock, take that 1 ticket, go into the other restroom, and, and they wait. So that's a scene from a Bollywood movie. So that's the basic bug. You just so that's the basic vulnerability bug. And so what we found was Amazon, in the case of Amazon, they have hardened Zen in some way so that we are not able to steal from other customers of Amazon, but we can steal from Amazon. So if there are not so many other customers that they are fully soaking up all the CPU on that particular machine, then you can steal from Amazon. You can get all the surplus. So even though you buy a small instance, you can get 2.5 times a small instance. Yeah.
So I guess maybe I'm speculating here. So for example, when you say you can steal from Amazon, but can you now make another customer essentially pay less? So for example, think of it as a simple memory bandwidth attack, right? So if I know that in your analogy, a resource verifier is going to come do the auditing/accounting, then I can issue a stream of memory stream requests to essentially eat up the whole memory bandwidth. And essentially, if there's another process that essentially is waiting to be serviced for those requests, and essentially that essentially explicitly you make that process paged or essentially temporarily suspended whenever this auditing is supposed to happen. So now and then essentially once that audit is gone, essentially you are paying yourself in a sense, but essentially avoiding.
I see.
Or making other processes pay less in proportion to what they should have.
I see. So you're saying flip it around, and instead of being an attacker, you become an altruist. You're a philanthropist. You keep getting charged, and you allow other people to run for free by timing. Yeah, you could do that. Yeah.
I mean, or actually, you may actually even save money in the process because you may be paying less than what the other customer is paying. Right. So essentially, since it's a
so you're saying somebody who's getting a discount from Amazon, they could pay more. You pay less in absolute terms, but more in relative terms, and subsidize another more expensive customer. Yeah, you could do all those games. Yeah. So that's a good point.
You have a business model in mind?
just thinking it's
yeah, you could resell. You could
probably resell it.
Yeah, exactly. You could resell it. Yeah. But again, though, from my sense is that I don't know if these numbers are correct or not, but apparently Amazon is not making much money on EC2. So when we were told them, you can, 10 cents, your people are paying you, they could, instead of paying you 25 cents, they could just be paying you 10 cents. It didn't seem like overly bothered or anything. So my sense is that at this point, it's not a big issue.
Do you know what their utilization is?
No, I don't know.
They may not be near, they may be under 50% utilization.
Right.
In fact, it's actually likely.
Right.
Yeah, I think normally we barely saw effects of other.
We ran at one time 200 instances in attack mode, and we couldn't find two guys on the same machine, so they're spread us so thin.
What you actually have is they're not relatively, they make a little money at 40, I think it's about 40% utilization.
Okay.
And they've been hesitant to up the utilization because they're afraid the quality of service will go down because they don't have to control that very well. But then the advantage they have is they can kind of do at least break even at not horrible, at not heroic utilization.
I see. Mm-hmm.
They're also sharing the infrastructure with their own services, right?
Yeah.
I see. So that's what I see. Okay, so
I think fair accounting, they still make money on EC2. Not a lot.
So I gave you the basic idea, which is fairly simple. I'll go into some detail now. So if you have switched off or you want to switch off, feel free. So there's a bit of terminology. So this is basically the Zen scheduler's flow diagram, how it operates. It's got a queue, and it gives people credits. And these people are in overdraft mode. They've consumed more than they should. These people are in underdraft mode. They still have some credits. And these guys, the boost guys, are the guys who have been boosted because they woke up or they got some I/O event or something, and so they're right at the front of the queue. And the scheduler basically takes the guy at the front of the queue, puts him on a core, and runs him for a while, then after some time takes away some credits from him, and then sees where he should be and puts him back in the queue, either at the end of the queue here, or if he still has some credits here, or if it's an I/O event here.
So if the virtual machine goes into an idle loop, they don't know?
No, so that they know. So here is this thing. So when this vCPU stands for virtual CPU. When a virtual machine is not running anything, suppose you have one. They do a hypercall called halt, and they trap into the hyper. So and the reason they did that explicitly is because they want to put it into a low power state. Okay.
You waste a lot of compute.
Yeah. Good. And so so this I've already explained. Credits arrive at a constant rate. They're conserved up to a max. So even though, so you can't keep accumulating more and more credits. Once they know you've reached a certain max, you stay there. What happens is the attacker stays at that max all the time. His credits never get spent. And the victims, they keep draining their credits till they fall to zero. But the scheduler doesn't refill everybody until everybody has gone down. But the attacker never goes down. He always has a credit, so he keeps getting run and run and run. Okay, and I can explain. Okay, so basically we are using a 1000 hertz kernel, so it's a 1 millisecond kernel tick. Every 10 milliseconds, the debiting is done. That's called the fast tick period. And every 30 milliseconds, new credits are allocated. So the max credits you can have is 300. So if you have, let's say, one vCPU, then every 30 milliseconds you'll get 300 credits, and every 10 milliseconds it'll come and take away 100 credits from that. Okay? So at the end of 30 milliseconds, you'll be back down to 0, then you'll run again, and that's how the system works. I won't bore you with details. It doesn't add greatly to the understanding. If you're really interested, you can look at the paper. I'll show you the code because it's so simple. So this is the cycle stealer code. So the main thing is there's something called the timestamp counter. Okay, so you can look at the CPU and see the timestamp or the number of CPU cycles. And our cycle stealer basically does the following. It keeps checking if we have we loop, we do whatever we need to do, we run for 9 milliseconds, okay, and then once we cross 9 milliseconds, then we go to sleep, okay, and as soon as we go to sleep, like I pointed out earlier, you do a halt, you tap into the hypervisor, somebody else gets scheduled. And they then are running at the 10 millisecond boundary. At the 10 millisecond boundary, the scheduler comes and takes away these 100 credits. It takes it away from the new guy. And then you wake up because you set yourself to sleep for something less than a millisecond, 0.5, but you'll be woken up at the next tick, which is on a millisecond boundary. And so you'll be woken up after it has come and taken the 100 credits away from the other guy. So you ran for 9 milliseconds, but the other guy ended up paying 100 credits, even though he ran for less than a millisecond. Okay, so that's the basic attack. And in the paper, we show how you can instrument this you can just basically insert this into dry stone. And you can do this in a variety of ways. So right now, we are actually looking at, okay, so suppose you have some code, some complicated piece of code. You can, at the binary level, you can go and instrument it by putting a bunch of sleeps. You can see how many steps roughly correspond to 9 milliseconds. Then you can put a sleep for 0.5 milliseconds and so on. You can sort of statically instrument your code so that you take advantage of this. You can build this into compilers or interpreters. Like you have a Perl code or a Python code. You could put it so that automatically the programmer just writes whatever program they want. But then the interpreter will put these sleeps in at the appropriate points, and that way you can steal cycles. And right now we are actually looking at doing this within the kernel itself. So you can, in Amazon, the kernel, you can load certain modules into it at runtime. And so we are planning to try to change things so we can keep track of how much it has executed and then put the whole machine to sleep for those 0.5 milliseconds. And the advantage of doing it that way would be that you could write any piece of code, any system you wanted, we would just run it on our modified kernel with this modified module, and automatically it'll do this sleep wake thing and consume more CPU. Okay. And we've had some other additional experiments. We tried running for 7 milliseconds and then sleeping for 2.5 milliseconds and so on. And earlier in one of the previous slides, I showed you there's a little attack overhead. So this is the attack overhead. If you run for 7 milliseconds and sleep for a little over 2 milliseconds, you only get 70% roughly. And then it kind of climbs up till about 9 milliseconds. After 9 or 9.7, 9.8, after 9.7 milliseconds, the resolution is not good enough. There's a lot of jitter. The operating systems are doing various things. The hypervisor is doing various things. We don't have very fine control. And what happens is, even if you try to sleep for a little bit, you may still get hit and get charged, and therefore your utilization come all the way down because you're not evading the charger. Okay. So then how do you fix this? So there are a few different fixes. Basic idea of a fix is you pay as much as you eat. So if you ran for 5 milliseconds, you pay 50 credits. If you ran for 10 milliseconds, you pay 100 credits. We charge you exactly how much you use. And so every time you go to sleep or you get taken off, we look at how much you have used at this point, and we charge you for that. So you can do an exact deterministic thing. You can do randomized things. You could, instead of making the ticket collector come at predictable points in time, like every 10 milliseconds, you make him show up arbitrarily. And you may have some short-run unfairness because he may you may avoid him randomly because there may be some variance in the system, but in the long run, it'll be fair, because if he's coming at random times, you can't evade him. And so we implemented a few different fixes that way. Bernoulli, where each millisecond you flip a coin and you say, should I go check on the guys now or not? So you modified the scheduler that way. This has a slight disadvantage that you could steal up to a millisecond. You could run 0.9 milliseconds and go to sleep, so it's a small amount you can steal. Then we made it a continuous variable, so the continuous version of the Bernoulli is the Poisson. And then for ease of implementation, because all of these things mess with the code a little bit, the code for the scheduler is automatically written on a 10 millisecond in a 10 millisecond framework. So you can also do the uniform scheme where you randomly pick a point between 1 and 10 milliseconds, go at that point in time, see who's running, and take 100 credits from them. Okay? So we implemented these 4 ways, and this is the result. So we are running in these 2. We are just showing you one is the cycle stealer, that code that I showed you. Another is versus with Drystone. That is, the attacking Drystone is the Drystone benchmark with this sleeps thrown into it. We run 1 attacker and 5 victims on 2 cores. So there's a total of 6 virtual machines on 2 cores. So each should get about 33%, 1/3 of a core. Okay? And if you use the unmodified Zen, then the attacker gets almost all of 1 core, close to 85%, and the others. And then with our fixes, you see that the attacker gets dialed down. He gets 32.9, 33.1, whatever, around 33%. The reason for the variation is because there are some overheads. When you have to flip coins and throw Bernoulli variables, you have to call rand and do all this, and there's some overheads with all of these. And as you can see, exact, which is the deterministic and perfect one, has a slightly higher overhead. If you do it randomly, you can reduce your overhead a little bit. And we just have a little chart showing the different.
What is the overhead for doing that? Do you have any idea?
They're in the order of 0.2%, 32.9 to 33.1, so about 0.1, 0.2. Just making calls to random variables, calling rand and getting numbers and.
Exact should be doing it, right?
Sorry?
Exact should just be looking at the system.
Oh no! Oh yeah. With exact, no, sorry. Exact. The overhead is that it has to do all this accounting. It has to keep track of. Okay, this guy ran for exactly 5 milliseconds, so I have to subtract 50 credits. That takes up some.
In other words, you're now worrying about a number of other locations during a switch that you weren't before. It was difficult to track down the precise.
Yeah, we don't. Yeah, we.
I believe the cache thing actually would have a big effect on cache performance, and as a result,
It restructured the data structures.
Okay, so and if you have more VMs, you have to maintain a list of all the VMs, who's running, then subtract, and so on. So I guess the accounting eats up some stuff. Okay, I have another 10, 15 minutes. Okay, so from this, basically, if you want to implement it, exact and uniform are the easiest to implement. Poisson and Bernoulli were a little more painful, and exact has some nice properties. It's 100% theft proof. It's completely fair in the short run, whereas the probabilistic ones, they may have some short run variance. Of course, long run, it's completely fair. You get what you should get. Okay, so we just put out these various fixes and analyze them. Okay, so now I'm going to go change into something that maybe David may find a little interesting, or maybe not. There was another paper by people from San Diego called "Hey, you get off of my cloud." The people here, yeah, rest in part. Okay. Good. So that paper, the major issue they were dealing with. Okay, so you have these virtual machines. You ask Amazon to fire them up. You can say, I want it in this region, in the European region, in this availability zone, but that's about all the control you have. You can't say which physical host that virtual machine is going to. And they basically, in their paper, argued that they can game the system. They can get virtual machines onto the same physical host. If they know that you're running on this particular physical host, they can do some things so that they get their virtual machine also to run on the same physical host, and then they can do side leakage from that virtual machine, and they can exploit it to their advantage. That was the basic story. In our case, too, I mentioned earlier, we have these 200 virtual machines we ran, and we put them all in attack mode, and in the wild, in the regular Amazon, we couldn't find 2 of them on the same core. It seemed like that spread us out real thin, right? But it would be nice if we are developing a system like this. Suppose we wanted, as a business model, we wanted to steal cycles from Amazon systematically. We would like it to be so that the attackers, we don't put 2 attackers on the same core. We would like the attackers to be spread out, right? Because otherwise they're just stealing from each other. We're just paying the attack overhead. So the question is the following. I want to learn the mapping. I want to learn, given a set of virtual machine instances, I want to know how they are mapped, which guys are going to which physical hosts. Okay? And so let me just state that formally as a theory style problem. These stars are virtual machines. These yellow boxes are physical hosts. There is some mapping. Okay? And the thing that we also noticed with Amazon is even though virtualization supports migration, they don't really migrate things. Once you start up a virtual machine instance, it seems to stay there. We ran it for days and it seemed to be there. We did a bunch of network tests and so on. It doesn't move, and that's also confirmed by the Rist and Part paper. They also didn't find any migration. So it looks like nobody is migrating anything right now, even though they claim they could. Okay, so we have some virtual machines. They're pinned to these physical hosts. I don't know which virtual machines are on which physical hosts. I want to find out this partition. So the problem is find this unknown partition. And what kinds of probes can I run? Well, I can choose a subset of my virtual machines to run. So I may choose this subset. I run this virtual machine, this one, this one, this one, that one, and that one. Okay, I don't run the others. So I run this subset of virtual machines. I run them all in attack mode. Now, if a virtual machine is running all by itself, it gets full 100%. Because it's running in attack mode, it gets. But if there are 2 of them on the same physical host, both running in attack mode, they won't both get 100%. They'll only get 50% each because they're both running full throttle. Okay? So I'll get back 1 bit for every virtual machine that I run, whether it's running at full power or it's running in degraded mode. Okay? So if I know the 2 guys, suppose I know that this said it's not running at full power, this is not running at full power, then maybe these 2 guys are on the same host. Okay? Right? So the general question is, find for me the unknown partition using the fewest number of probes. Okay? So just to make sure that you understand, the simplest thing I can do is run all possible pairs, all n choose 2 pairs, run every pair. If they are on different physical hosts, they'll both run at full power. If they're on the same physical host, they'll both run at half power. So I can tell for every pair whether they're in the same equivalence class or they're in different equivalence classes. And so then I can build up my partition. Right? With n choose 2 queries, I can find out. Okay? So the theory problem is, I give you an unknown partition, you can probe a set. For each bit in that set, for each element in the set, you get back a bit, a 0 or a 1, which says whether your set intersects the underlying partition in intersection sets of size 1 or greater than 1. Okay? And from that, you have to discover the partition. Okay? So, and then there's a bunch of ways you can do adaptive versus oblivious. Your queries, you may not want them to be adaptive. Means you get back the answer from one query, and then based on that you modify your subsequent queries. Or you may want oblivious queries, where you just throw your queries up front, and from that you have to figure out what the answers are. Some of you may know these puzzles like, I have 12 balls or 13 balls and 1 ball is of defective weight. How many weighings do I have to do to find out the ball which is not made of gold or things like that? And you can do either adaptive weighings where you weigh something, look at the answer, then weigh different things, or you could do oblivious weighings where you just do a bunch of weighings and then get the answers back and decide. Then you could put a bound on the number of virtual machines per host. So even though we have said we have parameterized this problem in terms of n, the total number of virtual machines, in reality you can only run a certain maximum number of virtual machines per physical host. Like, if you run more than 10 or something, the overheads of switching and everything eats everything away. And Amazon seems to be running no more than 2.5 virtual. They seem to be actually running at like virtually no one virtual machine per core is what we have seen so far. But and that would be like a 40% utilization. But presumably the most they can run is 10 for a 4-core machine. You could also have situations where you look at not just whether you're degraded, but how much you're degraded, so that you know how many of these virtual machines are colliding on the same physical host. You could look at randomized schemes versus deterministic schemes. You could ask for the explicit construction of the probe sets in the case of randomized. You could also look at time versus cost. So here we are looking at how many probes do we have to do. Each time you run a probe, you're paying Amazon some money, which is the number of virtual machines you're probing. And so you could look at the cost in terms of how much money are you paying to discover this partition.
So there's no easy way, if you write two VMs,
yeah.
There's no easy way to find out if they're on the same core without
on the same.
There ought to be some fast way to figure that out.
On the same physical host?
We were,
On our system, it's trivial.
I was going to say,
Yeah, Tristan, you know it, yeah.
read TSC we haven't actually checked that because it didn't occur until later, but it's possible given that it's para-virtualized, they can't virtualize the TSC. Well, they could.
Did you have one account with them?
No, we had a few.
They make you jump through a few hoops to do 200.
Yeah, because in one account you can only do 20.
I was thinking in one account they might
we had to call them up.
ones that account on different machines.
I'm sorry?
They might have tried to keep all the ones under a single account on different machines.
No, that they could have, but we used multiple accounts.
But they used your credit card.
Okay, so trivial upper bound is order n square. Just try all possible pairs and see whether they are on the same host or different hosts. A trivial lower bound is log n, because if you look at the number of partitions, there is 2 to the n log n partitions, and each query gives you back at most n bits. So the total amount of information you need n log n bits of information back. A query gives you at most n bits of information, so you must have at least log n query rounds. So that's just a simple information bound. For the case with, if you're guaranteed that your partition, no single set in that partition has size more than k, then we can actually do it in k square log n queries. And so the idea is to use a probabilistic method. You randomly select your query set and you filter small sets by doubling. So I will first pick a query set of size 2, then I'll try a query set of size 4, and so on. I'll keep doubling until k, until I do k, or get up to the size k. And then some probabilistic analysis shows you that with high probability, there will exist a query set which will be able to find out whatever the partition, it will be able to exactly get that partition. And so essentially, the main idea in there is that if you do the analysis, you'll find an s square term, and that actually leads to this k square. And you have to throw in an additional log n because that gets us the high probability for Chernoff bounds. So, okay. I can explain it, but basically you pick sets randomly. You take your first query set of size 2, then a 4, and so on, and you take a certain number of them, and then that will give you witnesses to whether people are in the same set of the partition or different sets of the partition, and you can put the information together and it works. And for the lower bound, we can actually boost the lower bound from log n to n over log n. Again, this is a probabilistic scheme. We show that if you have any query sequence that uses fewer than log n, then we will behave in a random way, in a certain particular random way, where we'll fix all the answers you're getting, but still retain the flexibility to have 2 different partitions. So that means you couldn't have narrowed it down to 1 partition. So that's the basic idea. And the combining a couple slightly more complicated ideas, not very complicated, but just a little bit, we actually can get the upper bound from, earlier I said you try all pairs and that's n choose 2. By using a slightly cleverer idea, we can actually get it down to n times n log n to the power 1/3. And there we are using this k square log n scheme, and we also have another scheme which gets it to n square over k. Basically, we trade off the scheme with the other scheme, and that gives us the 1/3 that you see.
Like the sieving bound for factoring?
No, it's not. It has not. There's no number. There's no primes. There's no numbers.
No, I know, but they trade off.
They trade off fine. Yeah, so it's the same kind of trade off. Correct. It's exactly the same kind of trade off, but there's no primes coming into this. This is just So we just trade off one algorithm's running time versus another, and we run them together. And so I am personally invested in this problem I'm curious to know what the right answer is, because we have a lower bound of n, the n over log n, and we have an upper bound of n to the 4/3. So I'm very curious to know what the right exponent is. Is it n to the 1 or n to the 4/3? Somewhere in between.
In computer science, that's pretty tight, actually.
So, okay, so that's this problem. Okay, so now just I'm finishing up. So we wrote up this paper, and then we submitted it to one conference, and it got rejected from there. And we were a little surprised and obviously unhappy. We found that in '93 there was a paper by McCann and Turek, which talks about this problem in the context of operating systems and processes. So we were completely unaware of it, honest to goodness. So the reviewer wrote about that. Then another reviewer in the same conference wrote about, or maybe it was the same reviewer, wrote about this.
Yeah.
This
Yeah,
paper.
I've seen that one.
You've seen that? And this paper doesn't reference that paper.
Well, in fact, they say they know nothing previous.
They say they know nothing previous. So this, you were aware of this?
Yeah, I'd heard of that paper.
Okay, so this basic idea of going to sleep when the resource verifier comes to check on you seems to be, I guess, probably there's even work before that. There's an obvious idea, so I guess. And then this is one related work, which we already mentioned. And this thing about this partitions and problems, I couldn't quite find the problem, so it may be that this is a new problem of finding the partition. But there's some things about conflict resolution in multiple access channels. There's things about people transmitting on a particular piece of the spectrum, and then they collide with each other if two people try to transmit at the same time, kind of like two VMs on the same physical.
Albert Greenberg?
Yes.
He's here. We could ask him.
Oh, okay. Oh, really? Okay. Oh, he's here? Okay.
Yeah.
Oh, cool. Does he still work on this kind of stuff? Or
He still works on networking stuff.
So this is the closest I could find. So actually, I might be interested to talk to him just to find out if this problem is solved already or not, because I don't want another surprise like that. So.
Actually, going back to the first year,
Yeah.
what that reminds me is, I don't know if it was ever published, like back in the early 70s actually, one of the attacks back in the US Air Force was to run your attacker such a short period of time such that it doesn't get recorded in the audit log.
I see. So the audit log comes at certain
Yes.
periodicity, and you just
Well,
you
yeah.
sneak in between there.
Exactly.
That's the same. It's the same idea. Yeah.
Yeah, it's the same. Any quantized granular clock.
Yeah.
You can, as long as you avoid the boundaries.
Right,
Correct.
right. Run within that period.
So my guess is that, yeah, maybe this is true of systems work in general. Everything is rediscovery. There is nothing original. So yeah.
For a VM hosted EC2, can you, do you have access to any fingerprint information of the physical host?
They can spoof all. Technically they can spoof anything. They can make everything.
They can virtualize anything.
Yeah, they can virtualize anything.
That's strictly true.
No, it's pervert. So CPU ID, for instance, I don't think they can touch that.
Really, they couldn't touch that?
Yeah, because
They could actually stop you from executing the CPU. I guess that's a user mode instruction. huh?
right. That's on if you're running with with hardware virtualization support, that's different. There's the whole bitmap of all the different operations you can trap on. But Pervert, you have very little. The only control you have for virtualizing things is things like the TSC. You can change them when you transition to the VM, but you can't trap any access.
So why didn't those UCSD people, those Ristenpart and co, why didn't they look at the CPU ID to figure out if they're running on the same or not?
That'll give you a quick filter for ones
Yeah,
that
it's
can't
not-
be, but
Right.
you're going to buy a bunch of identical machines and put them in identical.
They don't have
racks.
different, it's actually not really a CPU.
It's not like a-
CPU sort of ID.
Yes,
Sort of
It's stepping, it's up to stepping.
Yeah,
Ah.
it identifies which model, the features and everything.
I see.
It's more like a family ID than
Okay, so that's the answer to your
Well, I
question.
guess in more general, for example, like MAC address of the physical host.
That is all spoofable. All that can be spoofed.
Yeah, in fact, it is. That's how you get separate network interfaces to different VMs.
So VMware, I'm not VMware, sorry. Amazon won't assign hardware to you. They virtualize it. That's, especially for NICs, that's actually very expensive.
Okay, so and I should add that we are very grateful to Microsoft because John and Microsoft, they funded this research, and John has also played a big part in hooking us up with the Amazon security people.
And I gave him your credit card.
So thanks for that, and that's about my talk.